assessment. You know, the midterm is not going to be here. It's going to be in one of the auditorium. I forgot the name. Frankly, it does send an email and what that you have. Or that there is a bigger place, and it's going to be from. The reason I moved it from classroom over there is the time. You know, next year we only have 1.5 hours. That way we can give you a little bit more, maybe 2 hours, and or I have reserved it for 2.5 hours, but it's just you have some time. I will not be here for the exam, so I'll try to make the question as clear as possible. And you will start 5 o'clock. The location, she will send you an email. You will see where the location is in one of the auditoriums. And no class for Thursday and Tuesday. And homework 3, I'll send it to you. But the due date, you know, let's say you're going to take the exam next Thursday. Let's put it for Thursday after, for the homework number 3. Yeah. Thursday after the exam. You know. But I'll send you the homework. You know, I'll prepare it and send it to you. You know, you guys can work on it. Today you're going to start the induction machine, and in the discussion class session, I'm going to solve 2 problems. One on the rotating machine, and one on the motor starter for the DC machine. So, 2 problems. Any question?
So if there's no class Thursday, but how much do you do Thursday?
Thursday, you need to find time for someone to give the Thursday. I give her a little bit more time. You know, it's on you guys, you know, to find her. You know, to give her the homework by Thursday. What time is it? 5 o'clock. Do you want to sit somewhere they can come to get dropped off? So come here, or come here what time? Time for what time? 5 o'clock. So she will be here 5 to 5:15, you know, 15 minutes. You have to drop your homework here during that time, you know. And after that, don't send me please any email, hey, I cannot find way, blah, blah, blah. On the other side, 12 hours away. I cannot do anything for you, you know. So you 5 to 5:15, you should read your homework, okay? Induction machine. So we talked about briefly about the DC machine, how do they work, and we went through a different type of excitation. And if you remember what we said about DC machine, we started like this. We said they have a and we put a winding here, field winding. So this one is going to generate an N and S here, and this is one mag. This is one mag. And remember when we started electric machine, we said for every machine, for everything, to move you need 2 magnets, right? So the other magnet was here. When this guy, they have the current, they're going to create another magnet. So the N and S things, you know, from two different magnets, they're going to cause the rotation. Now for the AC machine, it's a little bit different. It's not as simple as DC machine. Look, let's start with this one first. If you have a you know, every machine has a winding inside, right? I'm going to talk about the sinusoidal winding. Let's see what's when I'm saying sinusoidal, you know, winding or distribution. What does it mean? Let's look at here. This is either a stator or rotor of the machine. The winding can be on the rotor part, like DC machine, right? We have the winding here, armature winding, or we would have field winding, right? So it doesn't matter which one. Here I'm talking about induction machine, by the way, they're not like this. See? This one, the stator is not cylindrical, it's inside the stator. Induction machine, they are like a 2-cylinder. One is a rotor, and one is a stator. 2 perfect cylinders. They're like moving part and a stationary part, right? We have a moving part and a stationary part. Now this winding I'm talking could be in the rotor or it could be in the stator. Just I want to say When I'm saying sinusoidal winding, sinusoidal distribution, what does it mean? Let's look at here. Let me put some slots here, for example. Let's say this is the stator, right? This is the stator. I'm going to put let's see what does it mean. When I'm saying sine, here there are slots. Basically, if you look at this machine here, it's like this. This is a cylinder with all these slots here, right? Let's define this one, for example, theta 0. Right? Let's define this one, for example, is theta 0, this axis. When we see sinusoidal, what's the sinusoidal? Right? At theta 0 is 0, at theta 90 degree is maximum, at theta 180 again is 0, to 270 is maximum, right? Now I want to put my winding in this system as a sinusoidal. So I'm going to look at n theta. This is the number of turns. Number of turns I'm putting in this slot. It's going to be equal to n sine theta, for example. Let's see what does it mean. Just I'm going roughly. How many conductor I'm going to have at 0 and 180? 0, right? It is sinusoidal. At 0, I should have a 0 conductor. At 180, I should have a 0, right? Let's go for the. Let's give this one a number, like 10. Let's make this one 10, right? Now, how about at 30 degree? How much is the sine theta at 30 degree? Is that 1 over 2, right? So 1 over 2 times 10 is going to be what? 5, right? Theta 30 is going to be 5. So, I don't know. For example, let's say here is a 5, right? Here is, I'll put a 5 turns here. 5 is going to be 1, 2, 3, 4, 5. I'll put 5 here. How about 60? How much is the 60? 1, 2, 3, 4. 90 divided by 4, how much is it? 22, right? 22. Actually, we go with the sine 22 basically. I don't know how much is sine 22. If you have, how much is sine 22? Somebody can calculate it. 22 and a half. How much is that? Yep.
Why is it 10 sine theta?
Huh?
Why is n of t 10 sine theta?
I'm saying I'm putting my windings like that. I'm designing this one. I'm putting this way to. I call it sinusoidal, distribution, sinusoidal winding. I mean, for example, at 0, I'll put a 0 turn. At 22 and a half, you're going to calculate it in a few seconds. How many turns am I going to put there? What?
0.8.
How much is it? Sine 22? 22 and a half?
0.38.
0.38. So 0.38 times 10 is going to be 3.8. We don't have 3.8 turns, right? We'll put 4, for example, here, right? We'll put 4 here. 4 here. How about 45 is the square root of 2 is a 0.7, right? 0.7 times 10 is going to be 7. I'm going to put 7 here. The next one is going to be 67 and a half. How much is 67 and a half?
So 9 turns.
9 turns. So it's going to be 9 turns. So we're going to be doing 9. And here I have to put how much? At 10. It's going to be 10 turns. Basically, this is the number of conductors, when we look at it. Now, if you look at it here, so I'll have one winding, it has a 10 turn, right? goes from here to, because here also should be 10 terms also, right? This is 270. I'll put 10 here, 1 here, right? I'm going to come to next slot. I'm not sure how many was, I think it was 9. 9 here, next, right? I'll go move it to this one. 7 and 7, right? Come here, 4 and 4, right? 0 and 0, right? Again, the same. They call this one sinusoidal distribution. The winding is going to be like this. If you look at it, you can say this is not continuous because the number of slots I have are limited, right? So basically, from here to here, you're going to see this 0, how much was here? 4, 7, I think 9, 10, right? I went from 0 to the 90, right? 0 to 90. Now I'm going to go here. It's going to be how much? 9, 7, 4, right? Let's look at it. It's going to be 9. Oh, this is a 10. Yeah, no, more than that. It's going to be 9, 7, 4, 0. Right? Now we're going to go negative, right? The same thing from here. This is very similar to the sinusoidal, right? It's not exactly sinusoidal, but very similar to sinusoidal. So if I say my winding is sinusoidal, means something like this, from this point. You just want to know. I want you to know what I'm talking about when I say sinusoidal winding is this. Now, let's assume we have a machine. It has a sinusoidal winding, and n theta is let's say we have a winding, and theta is, and I put it cosine here. This is sine, right? But you can change it and move it 90 degrees, then be cosine, right? If I'll put instead of theta 0 here, I assume theta 0 is here, right? It's going to be cosine, right? So I assume it is n cosine theta. I have a winding is like that. Current going through the winding. Current going through this one, I have theta, I'll call it theta. Theta is omega t, right? Theta is equal to Im cosine of omega t. Or we call this one theta, right? This is theta. So I have a sinusoidal winding. The sinusoidal current is going to, plugged into the wall, right? The sinusoidal current is going to this winding. Let's see what's going to happen. Remember from the magnetic circuit parts, right? We had HL, sigma HL is equal to Ni, right? So basically, let's say there's only one H here, right? So basically H is going to be this, right? And H is kind of proportional to what? B, right? So basically I can say somehow B is proportional to Ni, right? So my point is Ni. What kind of material is Ni? Is it like a magnet, right? B it shows like a magnet, right? When you have a magnet and S, you have this magnetic flux here, right? Right? So when you have an Ni also, it's like a magnet. So when you have an Ni, look at here, you have a piece of iron, right? You push current here, and you have N, this one becomes a magnet, right? So my point is, Ni is kind of like you can think about it like a permanent magnet, right? It's not permanent magnet, but you can think about it like a magnet, right? Now, let's calculate. I want to see how this one is going to be, right? I have a winding here. It's like that, and at any point I can say how much magnet I have. At this point I have this much of term, right? I have this much of current. Let's say how much of B I have in that place, right? So let's calculate Ni. It's going to be and make this one 2. Then half of NIN cosine of theta e minus theta plus, I think plus NIN over 2 cosine of theta e plus theta. And you know, what's this equation? This equation is coming from here. You know, cosine alpha, cosine beta, you can write it what? Half of cosine alpha minus beta plus cosine alpha plus beta, right? That's that. That equation. We call this one positive direction. This one we call it negative direction. Let's call this one F plus, and let's call this one F negative. This one represents a magnetic field which is rotating the system. This one is representing a magnetic field. If you look at it based on how much is the theta, it's going to have a different value, right? Basically, you can consider like a vector is rotating here, right? Based on how much this vector is rotating this way. The other one is like another magnet, but it's rotating other way, opposite down. That's the reason I call it positive and negative. So I have breaking down two magnetic fields. If I have a one sinusoidal winding with a sinusoidal current in the winding, it's going to end up like two magnets. One is rotating in the positive direction of the positive direction, one is rotating in the negative direction, right? Now keep this one in mind. So this is not good. Why? You have one magnet going this way, one magnet kind of, the resultant is kind of zero, right? It's not good, you know. We want to generate, you know, movement. Remember the first example I said, let's assume you have a rail here, you have a one magnet here, right? And you have another magnet here, right? If this one doesn't move, right? This one is not going to move, right? But if this one moves with a kind of specific speed, right? If this one is moved with a specific speed, this one also is going to start to move, right? Because N doesn't like N, right? They're going to start to move. So they need to move. These magnetic fields, they need to move to create one of them at least, to create a movement in the system, right? If they are standing here, nothing is going to happen. Yeah, they don't like each other. They're going to go to stand in some distance. They're not going to move anymore, right? But I want a motor. I want a generator. I want something to move, right? Now this is not good. One is going this way. One is going this way. Like right? So now let's see how we're going to get rid of one of them. If one of them is not good, if one of them is not there, perfect, right? Because I have one magnet is moving, right? One magnet is moving. So if I have only one of them, keep in mind, is good. But if I have both of them, is not good. If you look at all these small motors, like dishwashers, like laundry machines, those ones, they have all single phase machines. See, this is single phase. There is only one winding, right, and one current. They have this one. They fix this problem different way, not the way I'm going to solve it here now. They put a capacitor or something like that to generate a fake second phase, and the story is long. I'm not going to talk about it. But in three-phase system is very simple. How to fix this problem? Now the problem, I have two magnets. One is going positive, one going negative, and they're going to kind of cancel each other. I don't have a moving magnet, right? Now, let's see how I can do it. Now let's go. This induction machine, they are all three-phase. Now let's look at it. Let's say I have this one. I have NA theta is N cosine theta, and NB theta, I have phase A, phase B, and phase C inside the machine, right? NB theta